Perfect. Thank you. Well, thanks first for inviting me. It's really nice to be here. So I take this opportunity to talk about what we do in our group related to CO2-based electro-biorefineries. But first, I will introduce myself. If it works, yeah. So I did my PhD in chemical engineering, Newcastle University, with Eileen and Ian when she was in Newcastle University. And right after I started my almost short postdoc in Uwe Schroeder's lab in Germany, to Braunschweig. And since September 21, I'm a lead scientist at Helmholtz Center for Environmental Research in the Department of Microbial Biotechnology, which is led by Volk Harnisch. And since beginning of this year, I became a team leader in the same group, but as a separate team, working on which the name is Bioelectrochemical CO2 Conversion Team. The project that we're working with, which mainly I started in UFZ, is Vivaldi, as also mentioned, so which I will explain later on. So the group is called Electrobiotechnology. The head is Falk Harnisch, and we are the combination of scientists, PhD students, which come from different universities in our group, mainly University of Leipzig, but also technicians and master students. And we're working with national and international groups within different projects. But the team is part of this group exactly, which is led by myself, and we have different people that they are also joining. So for now we have Philip, our technician, Aykut, our PhD student, and we recently have a master student and a guest PhD student from Austria, and the PhD and the postdoc that they will join very soon to our team as well. What we do is we usually so the main focus is CO2 capture and conversion. And what we do, we basically develop electrochemical reactors for CO2 conversion, but with this idea to integrate it with biological processes. So that's why we screen and utilize engineered microbial resources, and we mainly focus on how to scale the processes, especially if we want to go towards industrial applications. We evaluate the system, and we always have we always consider new process lines for that. First, I will start with where we are, and then with biorefineries and how we contribute in that. So the current step of biorefineries is using renewable substrates, which we use for production, which we have pre-treatment by conversion separation, and our products are liquid, solid, and gas products, which they have different application later on. There are some challenges or shortages for the moment in this current current of biorefineries, which is first we have limited product portfolio from the biomass. Also, there are not much, as you can see, not much connection and linkage between the renewable electric energy with the current processes of biorefineries. And we also have a strong competition between the food and feed and what we fit into the whole system, and which we not necessarily use waste for that. But what we have also in our team, what we focus is we introduce electrochemical processes to hold these reactions, which means that, for example, what we can do is we can have one electrochemical reactions, which by that we can have power production from the renewable substrate for production of more renewable electric energy. But today, what I'm going to talk about, but also what this is the main target at what we do in bioelectrochemical CO2 conversion team, is we generate a chemical feedstock, and that comes from the waste, for example, from CO2 that we get, and also with the renewable substrate, and we produce different chemicals, not only the chemicals that we get from from the biorefineries, but also we can even improve the diversity of the products with bioelectrochemical processes. So by that, we have the diversity of the product, we have a strong linkage between the renewable sources of energy and these biorefineries. And the reason is that when we have electrochemistry, we need electric energy, and that can come from renewable sources of energy. And also for that, we don't have this competition that we had before between food and feed, and because we can use the waste for that. So we know that this can happen. We know that CO2 can go to the diverse portfolio of products, but we know that. So we have been like in different groups, people working on different aspects of this approach, but we still have challenges, and still these processes haven't reached to the higher TRLs than 4, for example. So I'm going to talk about two existing challenges that we see for now. One of them is the slow kinetics of the process and also the low efficiency. And for example, if we say that we have these two electrochemical and biological processes in one reactor, for example, they can disturb each other, and that may end up to low efficiency of the system. Or if we have the direct biological processes, which we have a biofilm formation at the electrode that we use in electrochemical reactors, this may take time because it's not usually a very fast process, and sometimes it takes very few hundred days. So we have these challenges at the moment, and what we can do, for example, one thing that we also we have in mind in our team is using the best out of these two processes, meaning that we can physically separate them and we can get the best out of, for example, high kinetics of electrochemistry, meaning that the CO2 that we have, we can be changed, for example, to C1 compounds, for example, as an example here, to formate, and then we can feed this formate to the microbes or any biological processes. They can be, for example, recirculated, or they can be completely separated to not disturb each other. So this is also our main target in our team, which we do that directly, as I mentioned, with biocatalysts at the surface of the electrode for the conversion of CO2 to the products, and we focus on how to speed up the process, or we can use chemical catalyst and convert it, as I mentioned, to C1 compounds, and after that we go towards different products. So this is the main target that we have in our group, and we work on different parts of it. So I will go through some of these examples that we have in the group. Also, this is in line with the project, as I mentioned, the Vivaldi project. So Vivaldi project is the European Union funded project, and it includes 16 European partners, and we're focusing on different parts and different work packages. And we ourselves in UFZ, we are the leader of the work package 1, and we are working with 3 other groups and in different countries. And the main focus is to, for example, from the Luleå University are responsible for purifying the CO2 in flue gas, industrial flue gas, and in UFZ we convert this electrochemically using the electrodes provided by Vito in Belgium, and also we have Aventium in Netherlands in case we want to separate for the downstream processes. And what we do is we produce these C1 compounds, for example, formate, and we feed it to the other work package that we're closely working with, which we do. They are 2 groups, BOKU in Austria and UAB in Barcelona. And what they do is they consume the formate. They use the formate in their fermentation reactors with the yeast engineered strains, and for production of different compounds, for example, succinic acid or itaconic acid. So this idea of separation of the processes of electrochemistry and biological processes actually is not very new. So this has been first reported by a group of James Liao in 2012, which they showed that CO2 can be electrochemically converted to formate, for example, and then it can be changed to biofuels using the microbes. And this this is how we started within our group. So this was done actually before I joined the group in 2017, and we started with a small scale, which was 50 milliliter reactor, and we started from there. And for that, we chose the catalyst that we chose was indium. The reason for choosing indium was indium is very formate selective from CO2, and what we came up with is how to we came up with the idea of electrodepositing indium on top of the graphite rod, and we always consider that all the condition we wanted to be biocompatible because we want to combine it with biological processes. So the first thing was make it completely reproducible and to make sure that we get a reproducible data. And you can see that these are the data for 1 hour for different timing in to different years, and you can see that each dot are representing each replicate. And it could show us that it actually can give us a reproducible data. But for that was at the beginning. And what we did afterwards, we started with optimizing the condition in terms of potential electrolyte, and we started with longer than 1 hour and the parameters affecting, but also this setup actually became the standard method in our group. So when we want to start different conditions or different catalysts, we always start with this method because it has been standardized very well. So I'm not going to go through all these conditions or all these studies that has been performed afterwards, but I can roughly show you, for example, the parameters that affect the over long-term operation. We started, for example, with 3 days, and we wanted to see that how this will affect the electrochemical CO2 reduction to formate. And we've tried it with different potentials, and we noticed that one of the challenges that we had, that after a while we started having some fluctuations in the results in the formate production rate and the coulombic efficiency, meaning that the number of electrons being changed to formate. And it showed that when we tried different control experiment for that, and I combined that with statistical analysis, which it showed that it's actually nothing to do with the electrode, whereas it seemed that the formate concentration and the change in the conductivity of the solution affected the actual potential of the electrode, which eventually affected the formate production rate and coulombic efficiency over time. If you want more information about other studies, actually the references are here. So then after that, when we had this reproducible data, we wanted to go towards larger scale. The reason is because eventually we wanted to go to the first higher scale, but also we want to be able to introduce it towards industrial applications. And in microbial or in biological processes, the minimum larger scale is usually 1 liter. And that's why we started with 1 liter, but it's actually, I wrote here 825 milliliter, because based on the design that we have inside, that is the volume of electrolyte that we can fit in. So for that, we started to design designing with different postdocs within the group as well. And we ended up with these reactors, which we call them electrobioreactors. And you can see that there are electrodes inside, and also this chamber, which is these windows are the membrane, and inside we have our counter electrode to make sure that the processes of counter and working electrodes are separated. And currently we're using them when we want to especially combine microbial and electrochemical processes. And for example, right now with our PhD student from Boku, she's running her experiments in these reactors as well. Then we compared the parameters between these two different scales, and we noticed that actually they are not very different. But for example, you could see that coulombic efficiency and formate production rate, of course, it dropped a bit, and that is usually expected when we go higher scale. So that was good news for us, and as I said, we always have this in mind to combine these two processes together, and for that we had this proof of concept with our colleagues in the Schema in Germany, which we combined the obligate aerobic of Methylobacterium with our electrochemical processes for production of C5 compounds. And for that, what we did is we started first, we had 2 phases. So the first phase was we in the electrobioreactors, we started having for 2 days electrochemical CO2 reduction to formate without having microbe inside. And after accumulating the formate in the system, we stopped the electrochemical processes. And then after that, we inoculate the reactor to be able to see that. And what we expected, that formate being consumed and the product being produced, which we have seen that as well, which was good. But when we calculated the efficiency, we noticed that the efficiencies were not high, so they were low. So first, that this was done in 2020. So after that, we were still working on that, and that we are improving the efficiency. But also for that time, it was enough for us to have this proof of concept and to show that products can be produced with only electrons and CO2. So for that part, that was mainly for how to combine these two processes, but also another challenge, as I mentioned, is the efficiency of the system. And if you go back to the literature, you can see that mainly the most common value being reported in literature is mainly coulombic efficiency. And usually authors, they claim that because their coulombic efficiency is very high, their system is very efficient. Actually, that is why one of our main focus is also carbon conversion efficiency. We also recently have some publications in energy efficiency, but it's not today's focus of this talk. So why we think that carbon conversion efficiency is important, because especially if we want to consider for industrial applications, we want to be able to convert all the CO2 that the industry gives us to the products that we want, not that the rest of the sum of parts be converted to the product and the rest goes back to atmosphere, and that's not what we want. And that is mainly the focus of this study that has been very recently published, that we showed that how important and how with very simple calculations we can improve the both actually mainly the carbon conversion efficiency. So for this study, we wanted to make sure that our setup is in the best optimal condition. And by that, I mean is first we changed the catalyst, because we were working with indium so far. And indium is in the list of critical raw materials in European Union. So that's why we changed that to tin, which is also cheaper, more accessible, and also it's still formate selective. And that's why Vito is involved here, because they give us the electrode, which mainly is with gas diffusion electrode. And that's the second optimization that we did in with our reactors, because we are dealing with gas form of substrate, and we don't want to worry about the mass transfer within our reactor. And that's why we have this study, and recently we kind of switching to gas diffusion electrode, mainly because to make sure that we don't have the problem of mass transfer. And that is how Vito is providing us with, for especially this talk that I'm having today, is all with tin GDE. So for this study, we wanted to first for calculation of coulombic efficiency, but also carbon conversion efficiency, we completely close the system, meaning that you can see that all the products in the cathode has been detected in line, and which is also recirculated. So we are sure that nothing is leaving the system. And by that, we wanted to measure the efficiency over 2 hours of operation. And so we use different catholytes, different concentrations of bicarbonate, and the reason is if you have a look in literature, there are different concentrations of bicarbonate. So I wanted to see what the differences are. And also we use the current of 100 milliamperes per centimeter. When we wanted to start the experiment, first we used the CO2 flow of 35 milliliter per minute. The reason for that was, again, going back to the literature, see that usually there is not specific reason. So it's very common using this flow of CO2 for electrochemical CO2 reduction. So that's why I chose that for the first set of experiments. Before starting the experiment, we needed to make sure that, because we had different concentrations of bicarbonate, so we wanted first to make sure that the conductivity is the same. But also we wanted to make sure that when we bubble CO2 over time, first is completely, in terms of pH, it reached to the stable condition. So that's what we did before starting the experiment, and the conductivity, as you can see, were adjusted, and they were close in all these conditions. So what we saw first is, you can see that in different concentration of bicarbonate, the column efficiency was similar in all these conditions, all these concentrations, and it was more than 85% for formate, and the rest went for carbon monoxide and hydrogen. But you can see that in all three other concentrations of bicarbonate, carbon conversion efficiency is only 20%, meaning that you can see that this blue color is the amount of CO2 we gave in the total 2 hours, and the green color is the one that we have in the solution. And you can see that in the outlet, what we got after 2 hours, we still had some CO2 going back to the atmosphere, just because they haven't been converted in the system. So what we wanted to do here is just to improving this efficiency, and by simply we just calculated how much CO2 we need, considering this current that we give to the system, but also this coulombic efficiency, and it needed just very simple calculation, and we came up with almost 16 milliliter per minute CO2. And when we ran this experiment with this CO2 flow, we learned that actually carbon conversion efficiency became twice higher, so we could increase it. We still had a bit CO2 in the headspace, meaning that it could not be converted, but the amount, you can see that is completely decreased, which was really good. And that is actually the main message that we have in this paper, to show that, and that by simply considering that this amount of electrons that we give to the system, we can simply calculate CO2, and we should not just give as CO2 as possible, whereas we need to measure that and see that how much we give to the system. Also, at the moment we scale up the system, and we want to consider all these efficiencies as well in different scales, in 10 times bigger and 30 times bigger, using the same electrodes from Vito. So these studies are still ongoing, but I will give you the very first data of the 10 times bigger reactors, which means that 100 square centimeter. And you can see that we tried it with two different, so the most concentrated and the least concentrated bicarbonate. And you could see that actually the coulombic efficiency was not similar as before. It was a bit lower, but again, it's actually usually expected when we go to the larger scale. So again, formate was high, the coulombic efficiency for that, and formate production rate as well. And very interesting fact was the carbon conversion efficiency, again by calculating simply that how much electrons we give to the solution, to the system, we got a similar carbon efficiency of the system, but we still got lower in the most diluted concentration of the bicarbonate, which this is just only the first data, and we are trying to understand why this has been lower in the other, which it was not the case in the smaller scale. So that is actually what we do mainly. This was a summary of what we do in terms of CO2-based electrobiorefineries, and I hope I could mention it, and I could convince you that we are working on what we are doing in our group, and that all what we do with combining, integrating electrochemistry with biology, we are trying to overcome the existing challenges in CO2 conversion, which because our main target is going towards industrial applications and going to the higher TRLs, which we have right now. And at the end, I like to mention that. So this is I just found it for example, light bulbs. And I noticed that, for example, the energy efficiency in the vintage light bulbs was around 10%. And over time, we can see that we increased to 85%, 90%. And that is what in our team, we believe that this can also happen for electrochemical CO2 conversion. Still, of course, for now, the efficiencies are low, but we believe that this can also improve over time. Yes, at the end, I'd like to thanks for your attention, and also thanks to our group and our collaborative partners, and especially Vito, and within the framework of Vivaldi. And I would be happy to take your questions if you have any.
Thank you very much, Paniz. I think yes, really interesting work. We have sufficient time for a few questions. May I ask if people online have any questions, please raise your hand. Maybe I can make a start, this is
Yes, please.
quite interesting work. Yeah. I think, I think I have a few questions.
Mhm.
Here is the first one is we have different routes. I think, for example, for CO2, you can make some simple products like C1 products like CO and use that at the syngas for the downstream synthesis of more complex products.
Mhm.
This route one, right? The other
Yes.
route is for example, we can directly convert CO2 to more complex products by electrochemical reaction. My question is, which one do you think is more promising? Maybe, let's say, which one is more closer to the commercialization? I mean,
Um, this is actually the conversation we usually have with Vito as well.
mm,
So I personally I think that it depends on what we would need to consider. If we want to go with a higher efficiency in terms of or higher production rate, for example, with when we scale up GDE, we noticed that for format production we could increase it massively. And so if we want to focus on the concentration of the product that we get, of course, for example, C1 compounds is it gives us because it's, for example, tin or indium are selective towards one compound. But if you want to go to the higher, for example, very diverse within electrochemistry, for example, if we use different materials such as copper, we have even more valuable products, but the concentration possibly is not because it's not selective towards one product. So I think that it depends on what we usually get. And at the moment, I believe that these C1 compounds, yeah, sure, they may not sound very interesting for the as in terms of price or in terms in the market, but
yeah.
when we have this always opportunity to feed it to microbes, and when we can get more valuable products, I think this sounds very promising, at least to me. But also everybody can have different opinion. Yeah.
Mm. Okay, good. Yeah, my next question is you just mentioned the scale up, right? I think this is very important because in the laboratory the size is too small and the electro size maybe 1 centimeter or 5 centimeter square in our research, right? I think for scaling up, what do you think the biggest challenge is?
I really, because we've just started doing scale up, and I really think
Mm,
that the main challenge is the technical, because for now we have some technical issues. For example, with when it's a smaller, of course, as we all know, so it's much easier to handle the reactor, but there are
mm,
some um, uh, issues comes up when we scale up, which we never predict that. And so I think for now it's that, but I think it doesn't mean that it cannot happen. Yeah, of course, I think any research has its own challenges when we scale up, but we are trying to solve them. For example, when we could get similar efficiencies, both coulombic and carbon conversion efficiency in the larger scale, I think this is really interesting. But also we had to solve some challenges in terms of technical issues, and especially if we want to introduce that to the industrial applications, first we need to make sure that we don't have these simple technical issues which we are trying to solve, especially like the balance of the pressure of, because we have gas substrate, so such things. But I think from there on, if we can solve that, which we did in the 10 times bigger scale, I think at the end it gave us a very good high efficiency and high production rate, which is really impressive for us.
Thank you very much. Yeah, I think we'd better to have other people online. Yeah, Eileen, actually, you have a question. That's good. Thank you.
Great. Hi, Paniz.
Hi,
Thank you
Eileen.
very much.
Thank you.
For yeah, it's great to see you, let's say growing up, become a group leader. That's very nice. So just one quick question. We still have the same problem
Mhm,
uh, with the toxicity of
mhm.
the. So have you actually consider that if you have particularly used tin, if you have actually kind of measured what is the like a leaching out of the catalyst into the formate?
Yeah, that's a really good question. So we have that with the smaller scale, we didn't have that much, but also it was only 2 hours. So we didn't have that much leaching of the tin in the solution. But when we did it, we changed it to the bigger scale. We could see it even by eye that we had this leaching when with the 100 square centimeter. But that is exactly our question as well, that because we're working for the moment, we're using indigenous strains and they are yeast, they are not bacteria. So we want to at the moment is in the under study to see that how they are they disturbing or not. So recently we sent the same solution to the group that we're working with to see that if the tin in the solution is toxic for their yeast, but also we have a PhD student, a guest student here, that she's also trying to understand that if that is that will be disturbing to the yeast or not. We expect that not be, possibly because of just yeast is a bit different from the bacteria that we were working with, but we don't know. So it's still we're still the study is ongoing, and yeah, but it is possible.
Yeah, that's great.
Yeah.
That's great. So yeah, maybe I'll send you email, and because recently, basically, again, we sent more formate to Oxford, so there are progress there, but still, toxicity is an issue. So yeah, I
I
think
remember.
we can. Yeah.
Yeah.
Okay. Yeah, we can discuss more. Yeah. Thank
Yeah,
you very
sure, for
much.
sure. No, thank
you.
Regarding the format, I have maybe a silly question. Is the format a very stable component, or that is a sensitive and it's very easy to be decomposite? Is that
So it is volatile fatty acids for sure, and it's also one carbon. So that's why we also have in our group, we have in our work package we're working with, we have also Aventium that they change it to salt as quick as possible, to change it to salt, and they try to remove it as a salt and send it back. But it is possible. So far we didn't have this much problem, especially when we calculate the efficiency. We noticed that we're still in the range, so we could not lose much. But also because our conditions are biocompatible, we don't expect to lose that much as we thought it would be. But so far, yeah, it was fine, and yeah,